Swayam Prabha. Digital India. Educated India.
Electron distribution inside a covalent molecule. Okay. Now, covalent molecules for the most part are neutral. Sometimes they could have a charge like carboxylate, ammonium, and so on. But for the most part, they're neutral. But that doesn't mean there's no charge distribution. So we're going to look at formal charges. Why do they call it formal charges? Because it's not like an ionic charge where you have a sodium with a full positive and a chloride with a full-blown negative, and where you stack up. Here you have electron distribution, and we compare that to a neutral atom because we want covalent molecules. The best form of a covalent molecule is a neutral molecule. And we want all of the atoms to be neutral. But sometimes electrons can shift around, okay? A little less, a little more. So we assign formal charges for these atoms. So what is a formal charge? A formal charge is comparing an atom in a molecule to the periodic table neutral element and seeing if it has more or less electrons than the one in the periodic table. So that is going to be formal charge. Is what's the difference between a neutral atom, so that is, let's say, group number of valence electrons, minus, so the delta electron, minus half of bonding electrons, of bonding electrons, plus lone pair electron. Not number of lone pairs, but number of electrons in the lone pairs. So you got 2 per lone pair. So basically this is 1 per bond and 2 per lone pair. That's what you're going to add. Or the bond is like a stick and the lone pairs are like dots. So you can see this is the easy way to do it. Valence electrons minus sticks plus dots. That's kind of how I do it. Sticks plus dots. If you have a double bond, that's 2 sticks. So here, let's find out how we can calculate that for different groups. Then we will apply them over here. So let's say group number, we don't have sodium and magnesium and group 1, group 2, they don't get involved in covalent bonding. So we don't have to talk about them here. But group 4 on, they do. So 4, 5, 6, and 7, and 8 doesn't get involved. These are the ones that get involved in covalent bonding. And formal charge is only for covalent bonding because ionic, you already know what the charge is. Calcium is +2, magnesium is +2, oxygen can be -2, chloride is -1. You already know all of that just from the group number. You don't have to do this calculation because there's no covalent bonds, there's no sticks and dots and stuff in ionic bonding. So this is only for covalent bonding. And then we have a very unique group 1 guy, which is, we put him in group 1, and that's hydrogen. And only hydrogen, not sodium. So I'm just not going to write group 1, I'm just going to write hydrogen. So group number is the number of valence electrons. So the valence electrons for all of them would be the same as the group number. Let me put it over here. So valence electrons for hydrogen is 1. And let's see, for group 4 is just 4, 5, 6, 7, where group number is the valence electron. So if you have one hydrogen, so for hydrogen, how do you know how many bonds you have? The number of bonds would be the octet minus the number of valence electrons that you already have. Hydrogen can go up to helium, 1s2, that's it. So maximum is 2 minus the 1 here. So that's going to be 1 bond. Carbon has got, well, this is going to be 4. So octet minus valence electron, 8 minus 4 would be 4 bonds. Okay. For group 5, like nitrogen, 8 minus 5 would be 3 bonds. Oxygen, group 8 minus 6, 2 bonds. Halogens, 8 minus 7 is 1 bond. This is going to be the number of bonds. So for hydrogen, you would only have 1 arm. For carbon, you would have, let's say over here, you have carbon here, and you would have 4 bonds. Nitrogen would have 3 bonds. Oxygen would have 2 bonds. And halogens, chlorine, bromine, X is going to be chlorine, bromine, iodine, and fluorine. So X would be just 1 bond. So we have all of these, then we have figured out how many bonds for all of these elements. Now if you go to phosphorus, it would be the same, or sulfur would be the same, and all of these elements would be the same. Now sulfur and selenium, nitrogen and phosphorus, and these halogens. If you go really to the bottom, like astatite and so on, then you're going to get ionic bonding. So this is only for that staircase and above, the elements above the staircase on the periodic table. Next thing we can do is find out how many lone pairs we need. So valence electrons minus the bonding electrons would be the lone pair. So over here, valence electrons minus the bonding electrons. So for every bond, you have 2 electrons. So here we have 2 electrons per bond. So valence electrons here would be again 2. Bonding electrons would be on hydrogen, there's 2. That's 0 lone pair. So a hydrogen never really has any lone pairs. So if you have hydrogen, that's it. You have an arm sticking out. Let's look at carbon. Valence electrons minus the bonding electrons. You have 2, 4, 6, 8 on carbon. So here you have 2 bonding electrons. Bonding electrons is 2. For carbon, you have 1, 2, 3, and 4. So that's 2 times 4. That's going to be 0. So no lone pairs on carbon if you have a neutral carbon. Now this is all for neutral. And 99% of the organic atoms out there are neutral. Nitrogen. So here you have nitrogen 2, 4, 6. So 8 minus 2 times 3, that's 6. 2. So you have 2 lone pair electrons. So that's how you calculate the lone pair. Oxygen. Oxygen has got 2 bonds, which we already figured out earlier. So then 8 minus 2 times 2, those are the 2. That's going to be 4. So you have 4 valence electrons that are going to be distributed as lone pairs. Where are you going to put them? Going to be on oxygen, lone pair. So you always have to put 2 at a time. All right. The last one, chlorine. So chlorine has got, we said, or bromine, iodine. You put 1 bond out here. So then 8 minus 2 times 1. You only have 1 of them. That's going to be 6, and we were going to put those 6 all around. So we figured out the number. So for neutral, this is going to be how it's going to look, because if you do formal charge for all of them, valence electron is sticks plus dots. Valence electrons minus sticks plus dots is formal charge. So over here, you have formal charge for this. is going to be valence electrons is 4 minus, and you count only 1 per bond. That's going to be 0. Over here, formal charge, same thing, group 5 minus sticks, 3 sticks and 2 dots in the box. 3 plus 2. All right, there you go. So that's also going to be 0. Over here, your oxygen, what's in the box? That's pretty much what formal charge is. So that's going to be 6 valence electron. Formal charge is valence electron minus sticks, 2, and dots, 4. So that's going to be 6 minus 6 is going to be 0. So you can see they're all neutral if they have this many bonds and lone pairs according to their groups. So here, formal charge again is going to be valence electron 7 minus, and here we are going to do the number of sticks and bonds, pretty much what's in the box. So that's going to be 1 bond and 6 lone pairs. So that's always going to be neutral if you have a bond on chlorine. This is going to be how a neutral atom is going to look in all of these groups. Let's see what would happen if we added a bond to each one of this. If possible, I'm saying if possible, because you cannot add a bond if it's going to exceed an octet on the first row. So here's hydrogen. Can we add 2 bonds to hydrogen? Never. Because hydrogen only has a 1s orbital. So maximum 2. Maximum 2 electrons. So therefore, this is never going to be possible. How about for carbon? Can we go in and add another bond? 1, 2, 3, 4, and 5. That's going to be 2, 4, 6, 8, 10 electrons. Complete violation of octet rule. So no, can't do this. How about nitrogen? Let's try this. So nitrogen has 3 bonds. Can we add 4? 1, 2, 3. And I'm going to put the next bond in a different color. Yeah, I still got an octet, so this is okay. What's the formal charge? All right, so now we took our nice lone pair and stretched it up and gave it to somebody like a hydrogen or a carbon. Now, when I draw these ticks, there are, invisible atoms here at the end of all of this, otherwise they won't be able to share that, right? You know that. So here, what's in the box? 5 minus ticks, no dots. So here it's going to be formal charge is 5 minus 4 bonds and 0 lone pairs, no lone pairs. So that is going to be a +1. So whenever you have nitrogen with 4 arms, it's always positive, always, because you can't really go wrong on that math. Oxygen, let's do an oxygen. So you take one of these lone pairs out and pull them out with an atom. It's called a dative bond. It's kind of dating that guy over there. So over here, this is 2, 3, 4, 5. So formal charge is going to be valence electron 6 minus 3 bonds and 2 lone pairs. So that's going to be a +1. So anytime you see an oxygen with 3 hands, it's too busy. So oxygen with 3 hands is always positive. Nitrogen with 4 hands is always +1. Carbon with 4 hands, on the other hand, is neutral. Nitrogen, let's say this is a lone pair with 3 bonds and a lone pair is neutral. Let's do the last one, chlorine Fluorine usually doesn't form two bonds because, you know, it's impossible. It's hard to pull electrons out of a fluorine. But chlorine, let's say you put two bonds. You take this lone pair and give it to somebody else. And so the formal charge is now going to be 7 minus 2 sticks and 4 dots. So that's going to be 7 minus 6 is a plus 1. Anytime you see a halogen with 2 arms, that's going to be a positive halogen with 2 bonds. What about if you remove a bond? What about if you remove a bond? Let's take hydrogen. Well, it has 1 bond. We'll take them off, and you can either do that and put them as lone pairs, or you can take the hydrogen and take it off completely, take off the bond completely. And here, formal charge for this is going to be, well, 1 minus 2, that's negative 1. So if you have 2 dots on a hydrogen, that's a negative 1. What if you don't have any electrons? Formal charge is going to be again 1 minus 0. That's going to be a plus 1. Okay, that's your acid. Plus 1, H plus. Carbon. Can we take off a bond? Sure, we can take off a bond. So, but then what do we do with those electrons? Let's say we have a carbon and we take off. We cannot add a bond because that's going to exceed an octet. But we can certainly take off a bond. Now we can take off the bond and put 2 electrons on the carbon, or we can take off the bond, and this is a special case, and not put anything at all. And they're both very significant. So here, formal charge is going to be, again, valence electrons 4 minus, and here there's 3 sticks and 2 dots. 3 plus, and so 4 minus 5 is a negative 1. Okay. Anytime you have carbon with 3 hands and 2 dots, it's a negative carb anion, we call it. Okay. And here, if you don't have any electrons, formal charge is going to be again 4 minus sticks is 3 and no dots. So therefore, it's going to be 4 minus 3 is going to be a plus 1. Okay. Carbon with 3 bonds has 2 scenarios, plus 1 or minus 1. And it's the same for hydrogen, guys. You know, you can see hydrogen can be either minus 1 or plus 1. Let's take nitrogen. Can we take off a nitrogen bond from here? Sure we can. So let's do a nitrogen here. So I'm taking off from here, from the neutral. I have 2 bonds, and I put one of them here. You already had one over here. So you're just taking off a bond and putting it there, and you want to make octets. Obviously, you don't want to take it off and not have an octet. Here we don't have an octet, that's true, but I'm just drawing this out because that's a very common intermediate that you're going to see. Okay. But here, you typically don't see nitrogen without an octet. So here, let's look at the formal charge. So formal charge here is going to be valence electrons, which is 5, minus sticks plus dots, 2 sticks and 4 dots. So that's 5 minus 6 is going to be a negative 1. So if you see nitrogen with only 2 hands, it's a nitrogen with just 2 hands and 2 lone pairs, but it's going to be just 2 hands here and 2 lone pairs. You are going to have 2 lone pairs here. You're going to have a negative 1. Oxygen, take the neutral and pull off the atom and leave the oxygen with an octet. Again, heteroatoms we don't typically draw without an octet. Carbon is the only exception. So formal charge for this guy, formal charge is going to be the same equation we apply every single time. 6 valence electrons, that's what it should have. But what does it have? It's got 1 bond electron. That's kind of, as I said, it's formal charge. It doesn't mean that oxygen doesn't share these electrons. In theory, these belong over here and to whatever is out here. This is part of a bond that we are drawing. Remember, these are bonds, and we are just not showing the other atom. So over here, this is just a formal application. So this is 1 bond plus 1, 2, 3, 4, 5, 6 dots. So that's 6 lone pair electrons. So that's going to be 6 minus 7 is negative 1. So you can see that this is a trend. When you add a bond or when you make the lone pair into a bond, your formal charge increases by 1. When you take off a bond then from your neutral, then your formal charge goes down by 1. It becomes a negative 1. Actually, it becomes negative. So here, let's do chlorine here, and we take off both. So then over here, you take off these 2 electrons here. And from the neutral, you remove a bond. And I'm going to say remove a bond from neutral. Neutral atom. From neutral atom. Not from the positive, it's from the neutral atom. So over here, this is just going to be your floor, your Fc is going to be 7 minus 0 bonds, 0 sticks here. And all lone pairs, and that electrons, that's going to be 1, 2, 3, 4, 5, 6, 7, 8. So that's a negative 1. So you know this is your chloride ion. So it's got a full charge, or a negative 1 charge. All of these have negative 1 charges on them. These have positive 1 charges on them. And this is a formal charge allocation. Now, we don't want to draw structures that don't have an octet in this quadrant, just because those are heteroatoms, they're more electronegative. It's just only for the carbon we can draw that. Okay, so once you clarified that and you got that down, now we can move on to doing some questions here, some practice problems. All right, let's do this. Lone pair. So here it's telling you find the formal charges. All hydrogens are shown. That means you can't go in and add any more hydrogens, but you can add lone pairs. To make octets, of course, why else would you do lone pairs, right? Add lone pairs. So that's kind of implied. So if you don't have an octet, let's add lone pairs. Over here, nitrogen's got 2, 4, which means it's going to have 2 dots, 2 pairs of dots, 2 lone pairs, 8. Oh, this is fine, 2, 4, 6, 8, and all the carbons are fine here. This oxygen, 2, 4, 6, so you need 2 dots here. And we already put 2 dots here earlier. And over here, this has only got 2 here, so you need to put 8. And we do lone pairs. 4, 4, nitrogen, 2, 4, 6, 8. You find bromine, group 7, 2, 2, 4, 6. All hydrogen should only have 1 stick. Over here, nitrogen, 2, 4. So then you need 2 here. Let's look at this guy here. Nitrogen, 2, 4, 6, 8. All these carbons have 4 bonds. This carbon only has 3. So over here, it says add lone pair. So we put a lone pair there. This nitrogen's got 4. This carbon's got 4. This nitrogen's only got 2. So we can put 2 here to do an octet. This has got 4. So we got 2 here to do an octet. Over here, let's see, you have this nitrogen's got 4. All of these have 4. This one's got 2, 4, 6, 8. They already put that for you. Right. Now let's find the formal charge. Do the same thing. Pretty much what's in the box. So all the ones there you added. If you didn't add anything here, here or here, that means the carbons are neutral. But this nitrogen has got what's in the all the heteroatoms. You have to find out. So let's box up our heteroatoms, and we can do a formal charge. Here's a heteroatom. Here's we forgot this guy, 2, 4, 6. So you need a pair here. 2, 4. Here's a heteroatom. So let's box up our heteroatoms. Carbon, if you have 4, then you know it's 0. So here's a heteroatom. Here's a heteroatom. Hydrogen, if you just stick, you know it's 0. Formal charge. Same here. All these carbons have got 4 bonds, so it's pretty obvious. So it's 4 minus 4. And this carbon's an exception. Here's a sulfur, and we forgot to put lone pairs on the sulfur. 2, 4, 6. That's a heteroatom too. So you got 8 there. This has got 8. Here's a heteroatom. Here's a heteroatom, and here's a heteroatom. Okay, and same here. 1, and this is the same as this. This is the same as that. And here's 1, and here's. We can do this as well if you have time. You can watch that. So here 2, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Let's do formal charges. Serving up formal charges here. Next, let's look at how you can calculate those. I mean, by now you should know nitrogen's 5, oxygen 6, guys, and okay. So and then halogens are 7, and carbons are 4. So that's 5 minus in the box 1, 2, 3, 4, 5, 6. 5 minus 6 is a negative 1. So this is a minus. Here 5 on a periodic table 1, 2, 3, 4 in the box. That's going to be a plus 1. So it's a plus, and here's a minus. Same here. Let's look at this. Oxygen 6 is in the minus what's in the box 1, 2, 3, 4, 5, 6. So that's a neutral oxygen. Over here, this is going to be 6 minus 1, 2, 3, 4, 5. That's going to be a plus 1. Over here, nitrogen 5 minus 3 sticks and 2 dots. So that's going to be 5 minus 5. That's a 0. That's a neutral nitrogen. I know you're used to seeing nitrogen like this, but you can have these 3 bonds as either a single bond, a double bond, or a triple bond, and it'll still be neutral. This formal charge is not just for single bonds. And same with oxygen. You can draw the oxygen out like this, and it is still going to be neutral. So these, I'm just drawing it out here. This is the same, okay. Oxygen here, 1 in the 1, 2, 3, 4, 5, 6, 7 should be 6. So it's a little bit more than what it should be when it's neutral, and therefore it's negative. Carbons are 4. Nitrogen here is going to be 1, 2, 3, 4. It should be 5, but it doesn't have enough, so it's a positive one. So this is negative, this is positive. Bromine, 1, 2, 3, 4, 5, 6, 7. 7 minus 7, that's 0. So when halogens have only 1 bond, they're going to be neutral. Let's go do these guys now. I think at this point you should hit the pause button, do it yourself, and check. All right, and so here's going to be nitrogen. It should have 5. It's got 1, 2, 3, 4, 5, 6. A little 1 too many. So 5 minus 6. That's a negative 1, so this is a minus. Sulfur is the same as oxygen, group 6. 6 is what it should have. It's got 1, 2, 3, 4, 5, not enough, so therefore it's positive. And this carbon here should have 4, but it's got 1, 2, 3, 4, 5 in the box. So 4 minus 5 minus 1. So if you have more electrons than you should have in the periodic table, you'd be negative. If you have 1 more, you'd be 1 negative. If you're lacking 1 from the periodic table, you'll be positive by now. That's kind of the take-home message here, and we see that happening over and over again. Let's look at this guy. Nitrogen should have 5. In the periodic table, 1, 2, 3, 4. Not enough, so it's a positive, right? nitrogen here should have 5, and it's got 5, 1, 2, 3, 4, 5. That's a 0. So this is a neutral nitrogen. This nitrogen here, 1, 2, 3, 4, 5, 6. We got one too many, so that's got a little bit too negative, -1. Same here, let's do this carbon is going to be 4 minus 5. That's -1. So whenever you see 2 dots on a carbon, it's in negative. There you go. Here's a nitrogen, 5 minus 4, that's going to be a +1. 1, 2, 3, 4. It should be 5, but it's only got 4, so it's positive. You can just do a positive like that, or you can write +1, or you can write +1, or you can just put a positive. And these two oxygens are the same, 1, 2, 3, 4, 5, 6, 7 in the box. It should be 6 in the box. 6 minus 7 is a -1, so this is a negative, so you can just write it like that. Same here, this is exactly the same as that. One more here, hydrogen, well, it's got to have 1. It only has 1. 1 minus 1 is 0, so if you have a hydrogen with a stick, it's a 0. Oxygen, 1, 2, 3, 4, 5, 6. So that is a perfectly fine neutral oxygen. Chlorine should be 7, 1, 2, 3, 4, 5, 6. The 7th electron is tied up with this oxygen, so therefore it's lacking 1, so it's positive. This oxygen's got 1, 2, 3, 4, 5, 6, 7. 6 is what it should be, and it's got 1 too many, so this is a -1. All right, so once you get kind of the hang of it, it's pretty easy to assign formal charges. What you have to be mindful is that you have to have octets for all your heteroatoms. And carbon, if you have a lone pair, is negative. If you don't have it, it's going to be positive. On all of the heteroatoms, if it is got the same number as the valence electron, it's going to be bonding electron, 1 per bond, lone pair electron, 2 per lone pair. When you add that up, if it's the same as the valence electrons, then it will be neutral or 0. If you have 1 more, then it will be negative. If you have 1 less, it will be positive. You can see +2 and -2, but they're so unstable that we typically don't write them. Even for, later on we'll learn about resonance, even for resonance we don't write them, but it is possible. So in summary, I just want to say that formal charge is a way of assigning the amount of electron density in an atom in an organic compound. And formal charge is the deviation from the neutral element, the amount of electrons an atom has that is either more or less than the valence electrons would give the formal charge. Obviously, if it's less than the valence electron, it will be positive. If it is more than the valence electrons, it will be negative because electrons are negatively charged. The easy way to look at it in a pictorial sense is to count the sticks and dots. Sticks are the bonds, so you count 1 electron per bond, and the dots are the lone pairs, so you count 2 electrons per lone pair. So formal charge is valence electrons minus half the bonding electron. So if you take a bond, it's just half of it, that's 1 electron, always. And then lone pair electrons, so therefore there's 2 per lone pair, okay? Anytime you have a atom, you draw a box around it, dot the sticks, dot the lone pairs, and count how many there are, and subtract from the periodic table value. So in this case, if you have this oxygen, you have 3 sticks and 2 dots, 5. Valence electrons for oxygen is just by the group number, so you could either say valence electrons or you could say group number. Number is the same as valence electrons. And then 6 minus 3 plus 2, that is going to be +1. So you can do the whole thing for any atoms as long as you know the number of bonds and lone pairs. And if you don't have all of the lone pairs on the atom, put them just enough to make octets, and then you can do your formal charge. All right? All right, we will see you soon. This is really important when you're trying to do resonance and seeing how charges are shifting in a molecule, or just to see the charge in a molecule. Talk to you soon.